right, guys, so I'm going to go ahead and say it's a sad morning. I don't know where my Apple Pen is. I think I may have left it at work on my podium. Not really sure. So we'll have to get through this without me being able to draw and point and highlight things as I do. So we'll see how this goes. Just stay with me, bear with me. I'm going to do it without my Apple Pen. Okay, so yesterday on the Zoom call, I went over some basic atomic structure and how to write nuclear symbols and what's really going on in terms of the overall structure of an atom. So today's focus when we go over nuclear reactions, we're not even talking about the electron cloud and electrons. We are literally just talking about that nucleus, because within that nucleus you've got protons and neutrons, and I talked to you guys about how the neutron's role is to kind of buffer the repulsive forces going on between the protons in that nucleus. So today we're going to look at what happens when the proton and neutron count start to become vastly different, and that ratio between protons and neutrons packed inside that nucleus starts to make the nucleus unstable. Excuse me. So all right, so an unstable nuclei. So the whole reason why nuclear reactions occur is because of a nucleus that has become unstable. So there are actually many nuclear reactions, but your textbook and this curriculum only covers 3 in this class, okay? So do understand, if we had more time, I would go over more of them, because I do find these to be pretty interesting. So as you can see, you guys can read, it says some atoms have a proton and neutron ratio in their nucleus that causes the nucleus to become or to be unstable. So they go through something called radioactive decay. So you guys have heard of elements that are radioactive. Yes, there are some that are much more unstable, and they will go through forms of radiation in order to become stable. So these are ways that the nucleus tries to fix that instability. So the 3 types we will go over is known as alpha decay, beta decay, and gamma release. And so anyway, this is the forms of releasing what are known as alpha particles. So you guys can see alpha decay is where alpha particles get released, beta particles get released with beta decay, that sort of thing. So let's move forward with that. All right, so this is a pretty busy screen, or pretty busy slide, and this was something that you guys can probably tell, this is my handwriting. This is something I put together. There was actually some guided notes that were posted on Thursday of last week, and you guys could actually fill this in. So if you did take the time to print off those guided notes or complete those, this is what I was looking for, is having examples of this. Okay, so it's a really good cheat sheet, something to look at in terms of having examples of each one and definitions. So all right, so what is alpha decay? Okay, so alpha decay is okay, so picture that you have this nucleus, right? And it's really, really unstable. So it's shaking with unstable energy, right? So in order to become stable, it shoots out this particle that is 2 protons and 2 neutrons. So this is this bundle, it's this little wad of protons and neutrons. 2 protons and 2 neutrons, okay? It's known as an alpha particle. So you've got this nucleus, and then all of a sudden it shoots out from it. And once it does, it kind of lessens that instability and helps to make that's the nucleus stable. So up here in this first example, so if you follow me on the first example, you've got radon 226. And so it's got 226 protons and neutrons total. Well, like I said, it releases. See how you've got the yield arrow? It's saying that once the reaction occurs, once it releases that particle, you've got an alpha particle. So you see the 4 and the 2 with the alpha symbol that looks like the little Jesus fish. That is that's an alpha. That's the alpha symbol, and that is representing that alpha particle that got released. So what happens is, whenever it releases those 4 protons and neutrons, 2 of them are protons. So notice that at the top, as a superscript, there's a 4, all right? And then at the bottom, there's a 2. Yesterday, we talked about how the superscripts represents P's and N's, protons and neutrons combined, and then the bottom subscript, the bottom exponent, or the subscript, the 2, that represents just protons. So you can see this alpha particle is representing the release of that particle's unit of 4 protons and 4 neutrons. Now, with that being said, remember, proton count identifies our element as what it is. So once it loses 2 protons, because remember there was 2 neutrons and 2 protons, you notice that the mass goes down to 222 in this, what we call this new daughter isotope, or this new daughter nucleus. You've got, I'm sorry, I said it wrong. We started with radium and then we ended up with radon. So you've got this brand new element. The whole reason we have a new element is because the proton count is now 86 instead of 88. And number 86 on the table is radon. Let me see if I can. Yeah. So this is radon over here. It's a noble gas, okay? And it started with as radium. All right, but it dropped down 2 atomic numbers. That is because it lost 2 protons, okay? So that's what we see. So a new element is created. The nucleus is now stable. So now, this decay or this radiation, so y'all heard of like how, like when people undergo like radiation for chemo treatments and stuff like that, that it actually hurts you. It's harmful, but it's designed to kind of eradicate poisonous or deadly cells. All right, but radiation, these are forms of radiation, and a lot of times they are harmful. Okay, so different types of radiation, some are more harmful than others. Okay, but they are a type of energy that particle that's released is extremely tiny. But in concentrated amounts, it can be harmful, this radioactive decay, this release from radioactive elements. All right, next. All right, so next is a beta decay. Okay, so beta decay is it's obviously not the same as alpha decay. It's a different type of radiation. So this is not when a nucleus releases 4 protons and 4 neutrons. That's an alpha particle, okay? That's the little alpha symbol that we see in the first equation right there. In beta decay is the release of a beta particle, okay? A beta particle has no mass, okay? So it doesn't weigh anything, and it has a negative charge. So essentially, it's like an electron, okay? It has no mass, it has a negative charge. So you can see in parentheses right there in Roman number 2 with beta decay that there is that symbol is the beta symbol. And you'll see the 0 is a superscript. That's because it has no weight. It has no mass. Now, at the bottom, that negative 1 is the charge that it has. So it has a negative charge. Now, just so you know what's going on in the nucleus, because we're talking about all of these are occurring because a nucleus is like unstable, right? Like it's like, oh, I need to get rid of this instability right now. I need to get this fixed. So in a beta decay, instead of releasing 4 protons and 4 neutrons, there is actually an internal transformation inside the nucleus. So what happens is a neutron, remember neutrons have no charge, okay, but they're inside the nucleus with the protons. It's when a neutron becomes a proton, okay, like literally inside of this nucleus, one of those ends becomes a P, all right. Now this is really when I really wish I had my Apple pen, but I don't. Anyways, so a neutron, think of this, a neutron is neutral, right? So think of a neutron as being a positive and a negative charge combined, and they cancel each other out. So if a neutron, okay, so it's neutral, so it's like, I'm not positive or negative, all right? I'm a neutron, I'm not positive or negative. Well, if I decide to become a proton, so now I'm a total proton, I have to get rid of that negative charge, okay? So that's what the beta particle is, okay? So what happens is when the neutron turns into a positive proton, it releases an electron to offset that change, okay? So let's look at this equation. Atomic mass does not change. Atomic number increases by 1. This should make sense. So let's say we've got a carbon-14 nucleus. All right, this is a rare isotope of carbon. And it's sitting here and it's like, oh, I'm not stable. And so then all of a sudden, in order to become stable, one of the neutrons inside this nucleus, we can't see it happening, but inside this nucleus, one of these neutrons turns into a positively charged proton. All right, so what ends up happening, so we look at the yield arrow, okay? When you look at that yield arrow, you'll see that the proton count has gone up to 7 now because one of those neutrons inside of the nucleus turned into a proton. Now the mass doesn't change because nothing left, like no neutrons or protons left. A neutron turned into a proton. So the mass, it still has the same number of protons and neutrons in it. It's just one of the neutrons turned into a proton. So that's where the 7 is developed. and why we now have a new element, atomic number 7, that's nitrogen, okay? Now, you also have to signify the release of that beta particle. It has no mass, and it has a 1 negative, okay, to represent or to signify its negative charge that's released. So beta decay is when internally one of the neutrons turns into a proton, transforms into a proton, and releases a negative charge to offset that positive charge that it now has. And it keeps the overall atom neutral. All right, so gamma radiation. This is the last one that we're going to talk about. Gamma radiation is the release of a gamma ray, okay? So this one is super easy, okay? So gamma radiation is just the release of energy. There's no particles, no charge changes, okay? It's a lot of times gamma radiation, not always, but a lot of times gamma radiation will accompany or will also occur with alpha or beta decay, with alpha or beta radiation. So we look right here at the bottom, it says a gamma ray has no mass and no charge. It is just released during high energy nuclear decay, okay? So usually accompanies alpha or beta radiation, not always, okay? So you've got uranium-238. So this is the the parent isotope or the unstable nucleus that we're starting with. Realize that in each one of these examples, that the element that you see to the left of the yield arrow that we start with, that is the unstable starting nucleus, okay? The nucleus of that element, that atom, is unstable. And then on the right side of the arrow, that is what we call our new daughter nucleus or new daughter isotope, okay? Now, uranium-238, right here in this example, it goes through 2 types of radiation. It goes through alpha and gamma. Now, look over here at the gamma symbol, okay? This is to the far right in the bottom example. All it is excess energy. It has no mass, has no weight. So it doesn't do anything really to the numbers. But you can see that this uranium-238 went through alpha decay because it's released an alpha particle. So this uranium-238, it's unstable. It releases an alpha particle, 4 total particles, 2 protons, 2 neutrons, okay? Releases that alpha particle, and then it's like, oh, I'm still not stable, and then it just releases a wave of energy, okay, an extra wave of energy. That's the gamma ray, okay? So it has no weight, it has no mass, has no charge. It just is excess energy. So it's almost like once a nucleus goes through alpha, beta, or some type of other radiation, it still has a little bit of excess energy it needs to release, and that's going to be your gamma radiation. All right, so let me look at, all right, so each one of these images, and this is in the PowerPoint, okay, that I went through. And so this is the alpha particle where I said that you've got this parent nucleus over here, the uranium-238. It's really unstable, and it emits 4 protons and 2 neutrons as what we call an alpha particle. Now you'll notice that it's got an HE for helium. That doesn't mean it's helium, okay? The reason why it's got a helium, so at the bottom, and it's hard to see this, but to the left where it says particle symbol, it can be written in 2 ways. It can have that alpha symbol with the 4 and the 2 on it, or it can say helium with a 4 and a 2. The only reason why is because a standard neutral ground state helium atom has a mass of 4 and a proton count of 2. So it's very similar to a helium nucleus. All right, so that's why it gets written that way. All right, so you can see it one of 2 ways. So this parent nucleus, it releases that, I know it's a weird noise, but I'm just trying to simulate this, that alpha particle, and then we've got a brand new daughter nucleus, a new identity. The mass has gone down by 4, which makes it, gone down by 4, so that makes the mass 234, but more importantly, the proton count has gone down by 2, which makes it a whole new element identity, which is number 90 on the table, which is thorium. All right, so an alpha particle is released from the nucleus. An alpha particle consists of 2 protons and 2 neutrons, which you can see in this image, and it is essentially like a helium atom, or a helium nucleus, I should say. All right. All right, beta radiation was where I told you guys that it does not release any mass. No protons, no neutrons get released. Inside there is, and you can see this image does a great job of kind of telling you that inside, and you can probably even look and identify which one of these actually turns into or changes color, all right, and turns into a proton. All right. Actually, I see it. It's right there. It's pointing. The arrow's pointing at it. So the gray little spheres are representing your neutrons. So you can see inside within beta decay, one of the neutrons just transforms into a positive proton, and so it has to release a beta particle, which is essentially just a negative charge, in order to offset that new adoption of a positive charge that it didn't have. All right. So you can see in this equation, carbon 14. This was the same one that I used in the prior slide, where one of the neutrons becomes proton. So now our proton count has increased, but the weight, the mass has not changed because we still have the same number of N's and P's. It's just there's, for instance, for this one, there is 6 P's and it starts out with 6 P's and 8 N's, 8 neutrons. But then once it changes and goes through the emission, it's now we have 7 P's and 7 N's. Okay, so the ratio of protons and neutrons changes to make it stabilized, but it's still the same total, which is 14. So you see the mass doesn't change. Beta particles also can be written 2 different ways. A lot of times you will see an E written instead of the beta symbol, because essentially a beta particle is like an electron. It has no mass, but it has a negative charge. All right, so that's why it can be written either way. So you can see it's got 2 ways that it can be written as well. All right, and then gamma radiation. So in gamma decay or gamma emission, you can see that there is, all it is just an excess wave of energy. It's usually accompanies alpha or beta decay. That's not always the case. So like right here, you can see you've got cobalt 60. You got this cobalt 60 nucleus, and it's really unstable. And then all of a sudden, it's like, oh, I need to release energy to get stable. And then it goes, and just releases this wave of energy. And now it's stable. It's like, okay. So that would be gamma decay. So normally occurs with alpha or beta decay, but can happen independently. It's just a photon, a wave of energy that once it's released, it helps stabilize the nucleus. All right, and so this last slide just kind of covers all of them together, and it's a lot of the same images that you guys already saw, so you can kind of look at this. You've got alpha, beta, gamma. So the equations at the bottom are something that we will start looking at more so. You guys have probably put together that when you look to the left and the right of the yield arrow, that the numbers will actually kind of add up or be equal. So that's something that's forthcoming, something that we'll look into when we do the Zoom call on Thursday, and actually break this stuff down and do some practice. So you guys have a mini quiz over what you saw today. You can go ahead and take that, and I will see you on our next Zoom call.